In the last part of this module, we get into reaction mechanism. And mechanisms basically describe, how the starting materials get transferred, right? So we're looking at the mechanics of it, how starting materials get, let's say, turned into products. Reactions can have a number of mechanistic steps in going from starting material to product. These mechanisms basically describe what's called the molecularity of the reaction, meaning, what molecule or molecules and how many are, imperative for the reaction to proceed. This idea of molecularity is related to reaction order. Right? So we're coming back to that reaction order idea again, and mechanisms help describe that idea of the molecularity of the reaction. And it's just basically showing us, how, these materials get turned into products. So it's really, it's like a hypothetical process, right? So the mechanism is really a hypothesis. For the mechanics of the reaction. Experiments can be done to determine a rate expression. Remember, we covered this earlier. In, part 2 of this lecture. So we've already done that idea that experiments can be done to determine a rate expression. The mechanism that is, postulated, must match the experimental, the experimentally determined rate expression. further experiments then can test the mechanism hypothesis. And maybe it needs to be changed, maybe it doesn't, right? Remember, with hypotheses, we can only disprove them or lend support to them. So that's the idea with this idea of mechanism, is that we can postulate it. We do an experiment, we get a rate expression, our mechanism needs to support that rate expression, and then further experiments can be done to test the mechanism hypothesis and its validity. So, those are the important features, right? It's a hypothesis. This is something that a chemist would envision of how the mechanics of the reaction actually work. Realize that when you're doing the experiments determine the rate expression, right? And so the mechanism that we postulate, has to be something that matches the actual experiment, because that's the real rate expression. And once we've developed a mechanism, then we would explore other reactions to see if that mechanism hypothesis stands up. Is it valid, or does it only work with certain models and not all models? And so that's the idea of trying to figure out, how the reaction proceeds from our starting materials to products. The connection between the two between the rate expression and mechanism is that in a mechanism, it is always the slow step that dictates the rate and rate expression. The starting materials that are part of the slow mechanistic step are the important players to the rate expression, and their stoichiometry is reaction order. The stoich really shows the molecularity of a process. Now, we have to be careful. This is solely for a mechanism. So keep that in mind, right? We're not talking about the stoichiometry of the reaction. We're talking about stoichiometry from the mechanism of the reaction. So keep that in mind. And so that's the big case here, is that it's always the slow step that dictates the rate and the rate expression from the mechanism, right? So remember, we're talking about mechanism. So it's the slow mechanistic step that's important to the players and the rate expression that we get. Remember, this is also a hypothesis, so this is something that we're just thinking up of how the reaction proceeds, and then we use other experiments to try to continue to support the mechanistic idea that we developed, or we find that, well, it doesn't work in all cases, or maybe we need to throw it out altogether. So here's kind of a running example here of 3 reactions and their experimental rate equations or rate expressions. We're going to use this example to learn how to develop a rate expression from a mechanism. So that's the important piece that we're going to be doing here. So let's say we have reaction 1. Reaction 1, we have methyl bromide here plus hydroxide produces methanol and HBr. And we find when we do the rate expression determination using our data, we find our rate is equal to little k times the concentration of the methyl bromide times the concentration of hydroxide. And, that seems to be legitimate, right? We have 2 starting materials. They both need to, run into each other, on a one-to-one basis to produce our product, right? I'm just thinking in the mechanistic, side of things. When I go to reaction 2, I kind of change the reaction a little bit. I change the starting material, but I don't feel I'm changing it that much. So I still have this, CH, this carbon bromine bond, and it's kind of, it's very similar to the molecule that we have above. Then we find the substitution that we see is very similar to what we had above as well. That, the OH swaps for the Br, and that's how we get transferred over to product. So we would expect the same rate expression. However, we find that the rate of this reaction is only equal to K times 1 of the starting materials. The other one is missing. Or it's 0 order. Remember, if it's 0 order, it's independent of the process. And then we have reaction 3, which, definitely looks a little bit different than the others. But seems like we're doing similar chemistry. We're just swapping one element for another. Here, swapping a bromine for a hydrogen atom. And we find the rate expression for this is equal to little k times CHBr3 to the first order, and then we have our bromine to the half order. So while I haven't really written it in, right, these are all first order processes. We could even add to this rate expression for reaction 2 to put in the hydroxide, but realize that it's actually 0 order. Oftentimes the 1 is left out because it's somewhat redundant, but just so that we're clear, it's all first order, and we can see all the starting materials, and sometimes we have dependence, and sometimes we don't have dependence. Since the rate expressions are all different. Right? This means that each reaction, basically goes by a different mechanism. So let's start to put some of these mechanisms down. Now, I want to stress that you're not able to really determine mechanisms. This is something that takes a lot of experience, right? Definitely takes a lot more understanding of chemistry and how things work. Bond energies and sterics, and there's all sorts of stuff to get into. So realize that these mechanisms are always going to be given to you, and then it's really what you do with them, right? As far as trying to develop the rate expression, or trying to see if this mechanism supports the experimental data from an earlier question or what have you. So let's go through each one of the reactions and actually develop a mechanism that's known for these reactions, and then we can talk about how we can relate that to our reaction coordinate diagram as well as our rate expression. So for the reaction 1, we were looking at the methyl bromide plus the hydroxide produces our methanol and our hydroxide, right? And our rate that was determined was first order in both the starting materials. So one way to envision this, right? Remember, this order is describing the molecularity of the process. So, we can think about just really kind of one molecule running into one molecule. If we look at, our molecules, we can draw them in a 3D sense here. I'm just trying to drawing them in their Lewis dot sense. But what we could, envision is, really these two molecules kind of running into one another. And so we could describe that process as maybe looking something like, this, where, and now just to try to give us a perspective, I'm going to draw this in a little bit more 3D, angle. If we look at that carbon atom, right, we would expect a tetrahedral. So here I'm kind of looking at it from the side. And what I'm trying to show here is the fact that, we're going to see, breaking of one bond and formation of another. So you have your hydroxide on one side, and you have your bromine on the other. And what we're seeing here is bond, breaking. And on the right side, we see our bond forming. So basically, the bond breaking is the same, or, we could say the extent of bond breaking is the same as our bond that's actually forming in the process. So that's the idea of the possibility of a mechanism. And then once we get over the hump, right, we now have our OH installed in the molecule. We just swap the OH for the Br. And that produces, the reaction mechanism, meaning that this is the only step. So it's the slow step. And if we then base our rate expression, right, remember we want to now base our rate expression of the mechanism on its slow step, the starting materials in the slow step, and the stoichiometry. So if we look at the very top, we have both the starting materials. They're 1-to-1. And from this, we develop our rate expression is equal to little k times the concentration of Br to the first order times hydroxide to the first order. These are our starting materials found in the slow step of the mechanism, and they are 1-to-1 in terms of our stoichiometry. So that develops the rate expression from the mechanism, and since the mechanism rate expression matches the experimental, this is a valid mechanistic hypothesis. So that's how we do it. If we scroll back to the mechanism, we have this weird little box that we have in the middle. We tend to have this double dagger relationship shown. What this is indicating is what's known as the transition state. So if we go to our reaction coordinate diagram, for this, right, we have our reaction coordinate. We're going to assume it's exothermic, just for our drawing. And so we would have our CH3Br, we would have our hydroxide, we would then have our products, the methanol and the bromide, and we would just have one hump going down to our products. Again, here is our activation energy, and this is our transition state. Right, that's the energy that we need to supply to get those two materials to come together. So that's kind of the idea of activation energy, is we had to add energy to bring the hydroxide in close contact with the CH3Br. We had to add, a little bit of activation energy to start breaking the bromine bond. We're starting to get some energy back with formation of the hydroxide bond. And then we go downhill to our products. So that is our transition state. And so we have one hump, since only one mechanistic step. And so that's the beginning of our understanding of reaction mechanism. Again, mechanisms will be given to you, so it's not like you have to come up with them. You don't have to worry about that. But you do have to be able to develop a rate expression from a mechanism, right? We already know how to derive a rate expression from experimental data, and it's that method that is the real rate expression. And then we can still develop rate expressions from mechanisms, but realize that those are hypotheses, and they have to, support the actual data. So here is an example of with reaction 1, how it's first order in both the starting materials, and a possible mechanism for how that transformation could occur. We could then experiment with other types of reactions to see how it holds up to those tests of looking at other starting materials, looking at similar transformations, but seeing how the rate and the rate expressions change. Now let's look at reaction 2's mechanism. Remember, the rate expression for this was first order in the bromine compound, but 0 order in the hydroxide. And so that means that, we must have, one molecule in the slow step. That also means for our other one that this should not be part of that slow step. So that's what that 0 order is describing, is the fact that the reaction is independent of its concentration. So a possible mechanism might look something like this. Instead of doing everything in one step like we did in the first reaction, we could maybe break it down into 2 steps, where we could say the first step is the breaking of the carbon-bromine bond. And we generate a carbon that is positive, as well as our bromide molecule or ion. And that first step, we will call the slow step. The next step would be then the formation. So instead of doing it all in one step, we could think about the mechanism happening in 2 steps. And this step would be really fast. So we remember, base our rate expression, from the mechanism and its slow step. Stoichiometry is order. And so if we go to our slow step, our rate would be equal to little k times the concentration of our bromo-containing molecule to the first order, and that would be it. And realize that's the same as what we got experimentally. So because of that, right, this mechanism supports the data. Right, and that's because its rate expression matches the experimental. So that's another way, right? Now a little bit more complicated with 2 steps, so we still base our rate expression from a mechanism on the slow step, the starting materials of that slow step, and then our stoichiometry is the reaction order. In terms of a reaction coordinate diagram, we now have some additional features. Again, we're going to, in this case, assume exothermic just for the diagram. So we have our 2 starting materials, the bromine containing the hydroxide. There's our starting materials going all the way over to then our products. We have the OH now containing molecule and bromide. And now we have these additional features, which is not 1 hump, but 2 humps. Before coming down to our products. And so we technically have, 2 activation energies. Here's activation energy 1, and that would be for the first step. And then here we see activation energy 2 for the second step. We have 2 steps, so that's why we have 2 humps. So that's why we have activation energy 1, activation energy 2. We have these transition states, and we have 2 transition states as well here. We can consider the first one, where that carbon-bromine bond is just starting to break. And then we can consider the second transition state when it's actually forming now the carbon-oxygen bond with the hydroxide. So those are the 2 transition states, and then we find something new, which is in the middle. And so this is known as an intermediate. And so intermediates are these molecules that actually have a lifetime, right? Meaning that there's a little bit of a well here, or a valley, in which some of the molecule gets stuck in right before they get enough activation energy to get over the second step. And so for intermediates, right, this is really just a molecule that is formed during one step of the mechanism, and then basically it gets used again. So it gets produced, and then it actually gets used up. And in this case, our intermediate would equal the carbon that has the positive charge. If we go back to our mechanism, we find that this is produced and then it's used. And so there's our nature of the intermediate, right? Because of that idea that it's just intermediary within the transformation of going from starting materials to product. It's produced, it has a lifetime, but at some point later on it gets used up. So our intermediate here is, again, that carbocation. So that's the reaction 2, right? So a little bit more, but we're still doing all the same steps as far as, how to take a rate expression and figure it out from the actual mechanism proposed. For the last reaction, reaction 3, we kind of start to really kind of up our game a little bit in terms of just more mechanistic steps. And we also add a new feature to to our repertoire, to our knowledge base. So our overall rate expression for this was CHBr3 to the first power times bromine to the 1/2 power. And our reaction was, starting with those two materials, and they were reacting to form CBr4 and HBr. And so this mechanism is definitely much more intricate, and also has an additional feature. So there was our reaction, just to remind us. And so for our mechanism, we have our first step with bromine splitting into two bromine atoms. This is a step that is fast. Notice that we have something new here with the arrows. We have a forward direction and we have a backwards direction. Then one of those bromine atoms takes a hydrogen to make HBr, and that is our slow step. And then the last step is the CBr3 combines with bromine to make CBr4, or carbon tetrabromine. And that's also a fast step. So there's our rate expression. There's our mechanism. And so now we have a little bit more going on here. So first step, right, we want to have our rate expression based on starting materials of the slow step, right, and their stoichiometry. Now, if we do that, we end up with a rate that looks like this. Now, when we get into more complicated features, we have to add another step to the process, right? We have to remember our experimental, the one that we determined via an experiment. Right, that's in terms of the true starting materials, or the real starting materials of the reaction. Right, the true starting materials for the reaction. If we go back to our reaction at the top, these are the true starting materials. the CHBr3 and the Br2. So we have to make sure that we're in terms of the true starting materials. If we look above, we find that the methyl bromide or the tribromomethane is a true starting material, but the bromine is actually an intermediate. So what this statement says is, it means that our rate expression must always be in terms of the true starting materials, never intermediates. So what does that mean? That means we then have to figure out where does that intermediate come from. So if an intermediate is in slow step, we have to go back to an earlier, step to see what its production is dependent on. If we keep going back, we will eventually get to a true starting material. So if we kind of just look at that mechanism again, I'll just redo it here instead of scrolling back. So here is, in terms of where we're at right now, here's our intermediate. So that's where it's coming from. So we have to go back to the actual now first step to see what the bromine atom is dependent on, and hopefully it's a starting material, and then we can solve the question, or complete the actual rate expression from the mechanism. So if we go back to that first step, we have something new. And so we need to kind of take a pause here and talk about, what equilibrium processes look like. And these are denoted by the forward arrow and the backwards arrow. These equilibrium processes are governed by KEQ. This is not a rate constant. This is known as an equilibrium constant. Equilibrium constants are capital K, rate constants are little k. And KEQ is always equal to the concentration of products over the concentration of starting materials. This has to do because of another definition within the equilibrium, which has to do with the fact that equilibrium is reached basically when the rate forward is equal to the rate backwards. And we're talking about forwards and backwards here as far as those arrows are concerned. If we think about it, we could actually write this in terms of a rate. Meaning that if we were looking at just going from starting materials to products, right, we could say that our rate is equal to little k times the starting material. And so let's call that maybe k forward. But we also have the other direction, meaning we can go from products to starting materials. So that means the rate could be equal to k, right, backward or backwards, which would be times our product. So we have these two rates, but they should actually be equal to one another as far as that forward direction and that backwards direction, right? Because that's the definition of our k. And so if I rearrange that just a little bit, right, and bring, let's say, my k's on one side and my starting materials on one side, right, by setting them equal to one another, because, right, at equilibrium, the rate forward is equal to the rate backwards. So my k forward times the starting materials would equal my k backwards times the products. And so if I kind of maybe collect the k's on one side, like I was saying, I get k forward over k backwards is equal to product over starting material. And that is our equilibrium constant. All right, so that means we kind of have to go back now to that mechanism. We've had kind of a crash course here in equilibria, which is actually the next module that we'll get into. But here, just introducing it with this nature of the mechanism. So let's get back to the mechanism. So just to re-highlight where we're at, we have the bromine as our first step. That was a fast step. We then had our slow step. And we had another fast step below it, but so that one really doesn't matter at this point. So just looking at this, and we were at this particular state where our rate was equal to k times the CHBr3 to the first power times our bromine atom to the first power. And so this intermediate is formed in the first step. And what governs that first step is an equilibrium constant. What is our equilibrium constant? Well, it would be our products over our starting materials. Right, remember? From above. And remember also with this mechanism idea, stoichiometry is also order. So we also have then the square there as far as the order with respect to the bromine atoms. So if I rearrange this expression, I can solve for this bromine atom concentration. All right, so now I'm able to figure out what that bromine concentration is dependent on by first rearranging it. Then I have to take the square root. And now I have what the bromine intermediate is in terms of. And so now we just substitute in for the intermediate. So originally I had my rate equal to K times the CHBr3 times our bromine, the first power. Right, this is what I'm doing now, is I'm taking that and substituting it in for that particular atom. So now our rate is equal to little k times CHBr3 times our first equilibrium constant to the 1/2 power times Br2 to the 1/2 power. So now basically all are true starting materials. So now basically we're done with the mechanism. All the constants are combined to produce a new constant. Or a new rate constant, little k. So if we then do that combination, we would have rate is equal to little k times the concentration of our CHBr3 to the first power times then our Br2 to the 1/2 power. And so it just so happens that this matches then our rate expression that we originally introduced. But then this would be, the rate expression derived from, our mechanism. And so it just so happens to support the experimental data. We can now look at this reaction coordinate diagram. Again, we're just going to kind of keep assuming exothermic for the nature of this drawing. And we have, our CBr, CHBr3, we have our bromine, we have our carbon tetrabromide, and our HBr products. And so in this case, we would see 3 steps. maybe see something that looks like this, where now we have, basically, 3 transition states because we have 3 activation energies. There's our first one. There's our second one. Right, there's our third one. Right, notice that activation energy 2 is the largest because that's the slow step. As a result, we have 3 transition states as well. These are when we're, kind of forming or breaking new bonds. For our transition state 1, we were, breaking the bromine-bromine bond. Transition state 2, we were really doing an abstraction. It's kind of a weird looking transition state, I guess, where you have the hydrogen interacting with the bromine. Don't worry, just so we recognize there are 3 transition states. We don't have to get into the specifics, but here we are breaking, and here we are forming. And then in the last transition state, right, we are now making or forming a bromine bond to carbon. So those are the 3 transition states which lead to the 2 intermediates. Right, so we have our intermediate, 1, which would be then, the bromine, right, that's produced. And then we have intermediate 2, which we would then be looking at, the CBr3. So, and that's just based on that mechanism. Again, we have, remember that idea of, 3 steps. So 3 humps in the diagram. Again, the tallest of the hump is, the activation energy with the slow step. And that's just kind of, that idea, right, that, it's really the slow step that bottlenecks the reaction, right? If you think about, a relay race team, right, they say your relay race team is only as fast as your slowest runner, right? And that's kind of what this means, so the slow step is the bottleneck. It's the one that really governs the actual reaction, since all the other steps are much faster than it. And so this is how we can put together now rate expressions from mechanisms, and then also how we can now design reaction coordinate diagrams to illustrate the energetics of the process in going from the starting materials to the products. And that is it for Module 14.